So in this lecture we will discuss method for handling missing values. So in data mining we might have situations where we have collected a certain data set but some of the values are missing. So maybe you collected measured the heights of a group of students and you forgot to measure some of the student heights. So maybe you could ignore the missing values, but it might turn out to be that doing so it's not the best strategy to go forward. So how can we handle missing values? So we can ignore these instances, but if those ignored instances are actually containing information about our target class, then we have no chance of learning how to classify an instance to that target class. We can fill the values by hand, we can measure these instances, but it's too slow and it's costly, it involves manual work, and it might not be even practically feasible if you don't have access to the original population that you used in the first place. So you can set a missing value constant that indicates this value is actually missing. It's a good value to set, for example, rather than setting the value to 0. If you have set the value to 0, then we don't know whether it was actually missing or it was actually measured and turned out to be 0. But it's not solving anything really. We can replace the missing values by the mean value of the data set. So that might be a good guess, because if your data is, for example, normally distributed, then the mean will have the highest probability. The chances are the data point that you missed was around from that the mean in the distribution. But if the data point is actually, the missing data point is actually an outlier and far away from the mean, so if you replace by the mean, in that case you will clearly be introducing some noise to the data set. So this is an example of an outlier where you can replace A by the mean of the reds, so that will work fine. But replacing B by mean of A or by mean of reds or blue groups is clearly not going to help. We can train a classifier to predict the missing values, assuming that the available other attributes have a particularly high correlation with these missing attributes. So this is a good example here where height and weight are highly correlated for a group of students. So you might guess that 168 of height would be something around 60 kilos. So we can, for example, transfer the missing value problems to the classifier that is operating on the data in the downstream of the data mining pipeline. And certain classifiers can actually do both, either predicting the missing values before they use the data for actual learning, or they can work with this missing value type of constants. The other problem in data mining that's closely related to missing values is the noisy value problem. So here we have actually measured the data points, and so nothing is missing, but our measurements contain certain amount of noise. Some noise could be quite obvious, you have just incorrect type in your data, or it could be sometimes quite difficult to detect, like typing 0.52 incorrectly, accidentally, instead of writing 0.25 type of things. So we can do manual inspection, but it's not doesn't scale up. And we could, for example, cluster our data points, and if certain data point is incorrect, then it will stand out as an outlier. Or we can, for example, learn a linear regression function, and then we can remove any data points that lie far outside this linear relationship. And there are certain ways of, for example, identifying noisy data in text mining applications. So one is if you rank your say features by their frequency, then these incorrect or noisy features would have a lower frequency, such as misspells. So there are various other issues as well with data normalization, where, for example, a certain person might have multiple namesakes on the web. So if you search for the name, you're just getting a collection of search results for the different namesakes. And the reverse problem also exists, where you can have aliases of names. And it might have redundant values as well. Maybe the same data point was measured multiple times. Certain classifiers, such as the naive Bayes classifier, can overestimate the conditional probabilities as shown here. So that is an adverse effect of having redundant values. So here's a quiz for you to try out, and you require to show that if we doubly count spam emails that contain a particular word advert, then we are going to overestimate the probability that seeing advert is likely to be a spam. So we have two types of problems in machine learning. One is called overfitting and another one is called underfitting. So if you train a model on your training data and it nearly perfectly kind of classifies your trained data, let's say with 98% accuracy, but when you apply it on your test data, you get a pretty much like a random classification decision. Say if it is binary classification, we get something like 51% classification accuracy. So this is because your classifier has overfitted to your training data. So in the case of underfitting, we might have situations where you don't actually get the performance even on the training data. So this could be because your training has not converged, has stopped too early. You need to give multiple more passes to your training algorithm. Maybe your feature space is not identical, it might be too small, it's not capturing the important properties of your training data. So you need to implement better features. Or maybe your training data is noisy and you need to kind of re-annotate your training data. Or maybe your algorithm is itself has a problem and it's not learning efficiently from your training data. If it is overfitting, then the case is that you will see high train accuracy but very less test accuracy. So you can add what is called regularization. So we will discuss this later on. You can stop your algorithm prematurely, thereby not letting it overfitting to your training data. So dropout is a technique that is used in deep learning. When you're training multi-layer deep neural networks, you always kind of like use 50% of your connections when you are learning at a time, and this 50% is determined randomly. So that way you make sure that your network makes robust classifiers.